Okay, on the board up there is a little chart about different things that are in the tree family. And they're divided in two categories, two ways each. So there's a kind of tree in which every node has a specific left child and a specific right child, and that's it. And there's a kind of tree in which a node can have any number of children. So that's the category that's labeled across the top, 2 children or n children. And then the vertical axis of this chart, you can build abstract data types for this kind of tree, or sometimes you're just using regular old pairs to make regular old lists, but you're using the ideas of this week about trees to think about those lists. So we've looked at the abstract data type capital T tree, the kind with datum and children as selectors. The book spends a fair amount of time on the binary tree abstraction. And we also talked about deep lists, about seeing a deep list, remember, as being a kind of degenerate tree in which the branch nodes have only children, no data, and the leaf nodes have only data, no children. And so we write programs, instead of writing programs like tree map that say make tree, something about the datum, something about the children, it's either or. We say if this is a leaf node, then do something about the thing viewed as a datum. If this is a branch node, which is to say it's a pair, then do something about this node viewed as a list of children. So the last piece of that chart that we haven't talked about is car-could or recursion, which I am going to get to, I guess, right now. So let's take my favorite list of lists. Okay, in the interest of time, I'm going to abbreviate. Okay, so this is a list of 4 elements. Each of the 4 elements is a list of 2 elements. And those things are words. Okay, everybody with me? So you got it that this is a list of length 4, right? And that each element of that list is a list. Now what I'm going to do is I'm going to grab this by its start arrow. I'm going to pick it up off the board and shake it. Okay? And the result will look like this. Wait, no, that's not going to work. I'm going to run out of room. Okay, so you see what I mean about picking it up and shaking it, and just sort of let gravity pull down this stuff, because this, if I pick it up over here, it's really right heavy. So its right end is going to swing down, right? Okay. Speaking abstractly, what does this remind you of? A binary tree, right? Every node has a left child. Every branch node, which is to say every pair, has a left child and a right child. This thing is more like a capital T tree. So deep lists, and this is how we viewed it on Monday, as a list of lists. If you think list of lists, it's like the capital T tree in that a node can have any number of children. This node right here has 4 children, right? And this one has 2 children, and so on. Here, it's more like a binary tree. There's a specific left child and a specific right child for every node, even though these are exactly the same structure, right? I drew the diagram differently, but if you follow the arrows, you will find that there's the same number of pairs and they're hooked up in the same way between these 2 diagrams. So what used to be the spine of the list is these 4 pairs, right? Okay.